All right. So for A, we are trying to find all of the fourth roots of 81i. We're going to use what we did yesterday, that de Moivre's theorem. My goodness. So all of the fourth roots of 81i. We're going to use what we did yesterday with de Moivre's theorem in order to figure out each of these. First things first. How many solutions are we expecting here? Okay, we're expecting 4 because we're taking a fourth root. So ideally, we should have 4 different answers here. Very good. In order to use de Moivre's theorem, what form does my complex number need to be in? Polar or rectangular? Polar, definitely polar. We need to have this be in terms of r and theta. To that end, we need to figure out r, which requires us to know what a and b are. So in this case, what is our value? So if z is equal to 81i, what is our value of a and what is our value of b? 0 and 81. And so r is going to be the square root of 0 squared plus 81 squared. And let's save ourselves some trouble here. The square root of 81 squared is just going to be what? Just 81. All right. So a little bit big, but it'll get cut down when we get our final answer. So no worries there. So we have our r. The only other thing that we need is our theta. What are the 2 equations that I can set up in order to figure out what theta is going to be? So the sine of theta is equal to cosine of theta is equal to. What is cosine of theta going to be equal to? 0 over 81, which is 0. Very good. And then what is sine of theta going to be equal to? It's going to be 1, which is from the fact that we are looking at 81 over 81, which is 1. So noting where this is all coming from, we've got r as 81. We've got a as 0. And we've got b as 81. What is the value of theta? That is going to give us an x value of 0 and a y value of 1 on the unit circle. Pi over 2. And so this z is the same as 81 CIS of pi over 2. Now, how many solutions did we say we were looking for? We said we're looking for 4 solutions here. And so how many other ways do I need to write this z here? I need an additional 3. Where do those other 3 come from? Coterminal angles with pi over 2. So we're going to take this theta, and what are we going to add to it? 2 pi, which may be a more convenient way to think about adding 2 pi would be 4 pi over 2. So we're going to add 4 pi over 2 until we have all 4 of our equations here. We're going to add it 3 times here. So z should also be equal to 81 CIS of 5 pi over 2. It should also be equal to 81 CIS of 9 pi over 2. And it should also be equal to 81 CIS of 13 pi over 2. All of these, this is all just adding 2 pi. right, if we are taking a fourth root, what power is that the same as? To the 1/4. And so z to the 1/4 is what we are ultimately looking for. According to de Moivre's, if I have z raised to a power, what do I do with r and what do I do with theta? So, yep, and then multiply the theta. Very good. So this is going to be 81 to the 1/4 CIS of 1/4 times pi over 2. This is going to be, again, z to the 1/4. I'll just go through all of these. 81 to the 1/4 CIS of 4th times 5 pi over 2. Z to the 1/4. Nine pi over 2. And lastly, 1 to the 1/4 CIS of 1/4 times 13 pi over 2. What is 81 to the 1/4? What's the principal fourth root of 81? That's going to be 3. Are there other fourth roots of 81? Yeah, in fact, how many would we expect there to be? We would expect there to be a total of 4. We're going to default to the principal one, though, for this, just to not get horribly confused. You probably could use the other one. I imagine that you could, or one of the other ones. I'm guessing that you could. Let's not. This is going to be, so we said that that's 3. My solutions that I get are 3 CIS of pi over 8. I get 3 CIS of 5 pi over 8. 3 CIS of 9 pi over 8. And 3 CIS of 13 pi over 8. As my 4 roots. Yeah. So when we multiplying pi over 2 can we just do You certainly could. So what are we basically doing here? Is that theta is equal to pi over 2 is what we found, but maybe reminiscent of what we did in 5.5. This is really theta is equal to pi over 2 plus 2 pi k. And so what I'm doing is I'm going through kind of similar to what we did in 5.5. I'm using k equals 0, I'm using k equals 1, I'm using k equals 2, and I'm using k equals 3 to get my 4 solutions. But that's not the only thing that we could do. We ultimately know that we're looking for 1/4 of theta. And so 1/4 of theta should be equal to pi over 2 times 1/4, which is going to be pi over 8, and then 2 pi k times 1/4, which should be pi over 2 times k. Same values of k is what you're looking for. You're looking for k equals 0, 1, 2, and 3, and that would give you the same solutions that we have here. So yes, you definitely can. But my logic for doing it this way is similar to the logic that I employed when we were doing 5.5, and I checked the values of k first before doing the division, just because fractions maybe make things a little bit harder. I don't know. But yes, absolutely, you can do the division first. Good question. Other questions here? All right, let's take a look at B as well. This was, we said Z is equal to 4 root 3 minus 4i. What quadrant does this live in? This is a quadrant 4 value. Didn't do this with the other one, but that was mostly just because it kind of lives in between two quadrants, and so didn't really want to mess around with that. But we're looking for a quadrant for theta here when we eventually do. We need our r and our theta again. Yeah, what's up, John? Yes, so we'll end up taking the cube root of z. We are ultimately looking for the cube root of z, and this would be like what we did here where we were setting it aside at first, and I just skipped that step. But you're correct. That is ultimately what we're going to do. All right, so what is our value of r? What did we find? I got the square root of 64, so this is 4 root 3 squared plus -4 squared, which is the square root of 48 plus 16. I agree that this is most definitely 8. What is cosine of theta going to be equal to? Root 3 over 2 or 4 root 3 over 8, which simplifies absolutely to root 3 over 2. And what is sine of theta going to be equal to? 1/2, -1/2 specifically. And so what is the value of theta? That gives us root 3 over 2 for x and 1/2 for y. We have Gabriella for checkout. All right, she's on her way. What's the reference angle that gives us root 3 over 2 and 1/2? Pi over 6, and then in quadrant 4, it's going to be 11 pi over 6. Have a good weekend. All right. So we have our r, we have our theta. Z is equal to 8 CIS of 11 pi over 6. If we are taking the cube root, how many solutions are we expecting? 3 solutions. And so how many additional solutions do I need for what I have here? 2 more. Let's add 2 pi to this theta twice. Adding 2 pi, what's maybe a convenient way to do that here? 12 pi over 6. I get that this is 23 pi over 6. I get that this is also 35 pi over 6. Is there anything that stops me from continuing, going more, adding 12 pi over and over again, 12 pi over 6 over and over again? Yeah, nothing like mathematical that's saying that I can't do it. It would just give us redundant solutions, right? We would get the same solutions over and over again. These are the 3 distinct solutions that we could expect to find. All right, cool. If we're taking the cube root, what power is this going to be? To the 1/3. So z to the 1/3 equal to 8 to the 1/3. CIS of 1/3 times 11 pi over 6, as well as with all of these others. I really do imagine that you could use any of the cube roots of 8 that we found yesterday, but what's probably going to be the easiest one to use? 2 is probably the easiest one to use, but I bet we could use any of them and get the same answer. I just am not willing to try that when we can just use 2. I am kind of curious now, though. I'm not going to lie. I bet it does. I bet it does. All right, so we said our 3 solutions, 8 to the 1/3 we said is 2. So this is 2 CIS of 11 pi over 18 2 CIS of 23 pi over 18, and 2 CIS of 35 pi over 18. All right, questions here with our bell work. Or just any questions with our complex numbers in polar form. So some cool applications of polar form makes what would otherwise be something that's impossible or really, really difficult a lot easier, which is nice. All right, we're going to move on to the final section for this particular unit. I will warn you, I am required by law to show you this video before we begin. It is just, they'll take away my license, they'll break my hands, I won't be allowed to do math ever again, and as tempting as that is, it sounds kind of painful, and so do know that this is not a choice that I am making, but instead is something that has been foisted upon us all. All right, where's my cursor? There we go.
I'm applying for a new film role. Go by the name of Vector. And the mathematical term, quantity represented by an arrow with both direction and magnitude. Vector! That's me, because I'm committing crimes with both direction and magnitude. Oh yeah!
All right. This is 13 years old, just by the way, which is kind of insane. Maybe that's less insane to you, but that's kind of very insane to me. So, this is actually a surprisingly very effective description of what we are going to be working with today, which is, and over the course of kind of the early stages of the next week, which are going to, of course, be vectors. Now, this is something that sounds very kind of difficult, or maybe if you've seen this in physics, something that is, very, very tricky. I would like to claim, and I'm going to spend the first little bit of class today kind of detailing to you, this is nothing new. These are objects that we have been working with since we have begun working with math, and a lot of the properties that we will find within vectors, a lot of the geometric properties that we will see, are going to be things that come from just math. And so, yeah, a very kind of hoity-toity way to define vectors is this way of it's an arrow and blah, blah, blah. Vectors are two-dimensional numbers, or they are three-dimensional numbers, or they are one-dimensional numbers, or they're just numbers. They're just numbers that can have a higher dimension than just a single directional input. Which means that the numbers that we have worked with, kind of, certainly can be thought of in the way that we think of vectors. We can conceptualize all of what we have done in terms of working with vectors. So I want to kind of highlight that. We are going to primarily be focusing on vectors in 2 dimensions, but we're just going to start with a little bit of an introduction to them in terms of what's going on in our 1-dimensional case. Call this 0. All right, and I have done a poor job of spacing, but such is life, that is fine. So let's say we were trying to explain to someone the idea of kind of this basic number line. And this person, for whatever reason, was very, very interested in getting to 3 from the number line. Now, what we're going to find is that there are a lot of ways that we could instruct them. But if we fix our starting point, there's really only going to be one set of instructions that we can give. If I'm starting from the center, if I'm starting from 0, how would you explain to someone how to get to 3 from that kind of initial point of 0? Okay, very good. So we would start at 0, we would move 3 kind of notches, 1, 2, 3, to the right. And what we have just communicated there is a direction and a magnitude. The magnitude is the number of spaces. It's the size of the movement. So in this case, we said move 3, which is our size of movement. It is also the absolute value. It is also the magnitude that we have looked at with regards to what we're doing. It's just how far we have to go. The direction, which is also very important, was the specification that we are moving 3 to the right, which is our direction. So we have the size of the movement, which we are going to think of as the magnitude, and we have this very simple direction. We could have moved 3 to the left, and that would have taken us to a different terminal location. We could have also, well, actually, that's it. We're in one dimension, so we only have those 2 options of moving to the left or to the right. And those will give us both unique vectors, noting that like the difference, say, between starting at 0 and moving 3 to the left, very obviously gives us a different, gives us a different endpoint than when we are moving to the right. And again, my spacing's a little bit poor here, but we would expect these to have the same magnitude, but be pointing in different directions. Now, alongside this quantity of vectors, and whenever I'm referring to a number as a vector, I'm going to put a little arrow over it just so that we know that it is a vector that I'm referring to. So maybe rather than referring to this just as 3, maybe I'll refer to it as like 3 with this little arrow on top. 3 with the arrow, just so that it's like the vector 3. In addition to vectors, there is another class of number called a scalar. Scalars do not contain as much information as vectors, and rarely do we ever see scalars on their own. Not that it's impossible to have scalars on their own, just that generally speaking, when we are working with values, when we're working with objects, scalars are kind of their own separate thing that we pull from to modify vectors. An example of a scalar would be like taking the vector 3 and maybe multiplying it by 2. This 2 does not necessarily have direction on its own, although we'll examine that idea here momentarily. It's instead telling us to do something to our vector what would multiplying our vector by 2, what would you guys think multiplying our vector 3 by 2 would do to it? Increase the magnitude by how much? To 6. It would double the magnitude. And in fact, that is exactly what we see. The length of this vector is modified to have a length of 6, which is notably 2 times the original. All right. This is called scalar multiplication. It's really it's not the only kind of multiplication that you see with vectors. It is the main source of multiplication. There are 2 others, but they don't really act like multiplication in the sense that we will think of them. We'll examine one of them at the end here. And what that is going to be so thoroughly underexplored for this class. And it's really more just so that you know that it exists. But we have ways that we can kind of multiply vectors. We generally don't, not that we generally don't, but they don't give us this, they don't give us vectors. The way that we multiply with vectors is through what is called scalar multiplication, and it is exactly what we see here, and the effect is exactly what you would expect, where if we multiply a vector by 2, it is going to double the length of the vector. If you were to multiply a vector by 1/2, it would cut the length of the vector in half. All right. In particular, noting that this 2 is changing our magnitude and not our direction, can we think of a scalar multiple, a scalar that we could multiply that doesn't change the magnitude and only changes the direction? -1 is going to be the one that does this. If we think of what's going on with -1 times our vector, this is not changing the length at all, but is instead giving us a vector with the same length in the what I would classify as the opposite direction. So this modification, this multiplying by -1, is simply rotating us by 180 degrees. Actually, this is a really good way to think about it. Multiplying by -1 is a 180-degree rotation, or you could think of it as reversing our direction. We're going to see that that is true in not just our one-dimensional setting, but also our two-dimensional setting, and probably to some degree the three-dimensional setting, although at that point I'm guessing it's rotating the phi and the theta by 180 degrees, and we're not going to worry about that because we're not going to look at three-dimensional vectors, but I'm guessing it would have that effect. All right, so as far as vocabulary, we have our vectors. These are going to be quantities that have both a direction and a magnitude. We have our scalars, which are quantities that do have a magnitude, right? There's a difference between multiplying by 2 and multiplying by 1/2, but they don't really necessarily have the sense of direction. And generally, we don't see them on their own. Oftentimes, they modify a vector. And there are kind of two classifications to this modification. We could see it change the length of the vector, pretty much exactly how you would expect. Again, multiplying by the scalar of 2 will double the length of the vector. Multiplying by 1/2 will cut the length of the vector in half. But we can also see it sometimes change the direction if that scalar is negative. So multiplying by a scalar of -1 will adjust the direction instead. But it only inverts the direction. It can't like rotate us by 90 degrees. Scalar multiplication is not capable of doing that. We are going to be along the same line. It's just, will we be going up the line or will we be going down the line? Mm-hmm. Yes, exactly. And Shruti has just made a really, really good point here, which is that when we multiply a vector by a scalar, the result is another vector. So in particular here, the scalar 2 times the vector 3 results in the vector 6. Good point. And it'll have that effect in 2 dimensions as well. It's exactly what you would expect when we scale it up. All right, questions with our kind of basic definitions here? Yeah. Sure. Something that I think is kind of interesting to highlight, if you have ever wondered why multiplying 2 negatives together gives you a positive, it is because multiplying by -1 is going to reverse your direction. So if you have a vector that is going to the left and you multiply it by -1, it is going to flip and be pointing to the right instead, which is why 2 negatives multiplied together will give you a positive. In as far as we are doing scalar multiplication. I guess it doesn't explain why 2 negative scalars multiplied together would give us a positive scalar. But that also isn't too hard to explain. It's because you're reversing direction and then reversing direction back. And so the net result is you don't change the direction. So actually, it does do a good job of explaining both of those. All right, we'll come back to the actually, no. While we're here, we'll talk about this as well. So we have scalar multiplication with our vectors. The other thing that we can do with our vectors is we can add them together. For instance, we could think about what happens if I take the vector 2 and add it with the vector 3. Right? What would our prediction be for the result here if this is working like I'm claiming that it should, that these are just numbers? Should be the vector 5. And in fact, that is exactly what we're going to see. If we start at 0 and travel out by 2, and then from that new location, starting here, travel out by 3, then the net movement that we see is indeed the vector 5. So questions with our one-dimensional kind of base case here? Is that a question, sorry, or just flexing? Gotcha. All right, let's scale it up. We're going to look at some, and we're going to focus mostly on 2-dimensional numbers. A lot of our findings, though, would also work in 3 dimensions and 4 dimensions and 5 dimensions and so on. We're not really going to focus on those, but if you take like a linear algebra class, that would be like the next steps, is the vector things that we find here will work pretty universally, which is kind of cool. Or at the very least, they have like analogs in the other dimensions that work very, very well. When I'm saying like 1-dimensional versus 2-dimensional, by the way, this is just like It's very much your colloquial notion of like the number of directions that we can move. So if we are living in one dimension, then we can move to the left or to the right. If you add another dimension, then you can move up and down as well as to the left and the right. A third dimension would be like forward, back, left, right, and up, down. So it's like the number of directions that you can move. So two-dimensional case, we have not just X movement possible, we also now see that we have Y movement possible. All right. Again, we are going to assume, although we'll see pretty quickly here that this does not need to be the case. Again, we're going to assume that we're going to start at the origin. And in this case, I want to think about the vector that ends at the point 2, 3. In this case, what we are looking at is a vector that moves 2 to the right and then 3 up. The way we are going to denote this vector is pretty similar to actually how we write the point 2, 3. Slightly different though. So instead of parentheses, this is going to be these little pointy arrow-esque parentheses, 2, 3. It's really important to note here that what is defining this vector is specifically the movement. There are a lot of ways for us to get to the point 2, 3. For instance, if we started at 1, 1, the motion that we would have to follow to get to 2, 3 is different than if we start at 0, 0. And it's different than if we started at -10, -10. And it's different than if we started at 4, 4. And because of that, the ultimate thing that the vector is trying to capture is the movement. The vector doesn't really care about the starting location and the stopping location. The vector only cares about the magnitude, what distance are we traveling, and the direction, which theta are we going to be moving in. So for instance, if rather than starting at the origin and ending at the point 2, 3, I started at the point 2, 0 and ended at the point 4, 3, which, again, my art skills are maybe not being particularly convincing in this case. There we go. That looks about right. We will notice that we get the same vector. And it's not that these are like similar vectors. They're literally the same vector. They are literally thought of as the same vector. The actual location of the vector is not relevant. I could move this anywhere I wanted to, and it would still be the same vector as long as I am not changing how long it is, and as long as I am not changing which way it is pointing. And we're going to mess around with some stuff. This is important to the idea of how we add vectors, but also this is just kind of the way that we think about it. What we have written here, there are a couple of ways that we're going to see that we can write out what a vector is. This kind of most basic way with the 2, 3 is called the component form of the vector, which again, very, very similar to a point. And the way that we can kind of think about it, again, the vector is implying some kind of movement from start to stop. The way that we can think about component form is as some kind of change in x, my x movement, and some kind of change in y, my y movement. That's a pretty good way to think about this. It's like some kind of change in x, some kind of change in y. We definitely could put an equation to this, but I think just kind of looking at these and saying, okay, well, what is it going to be is fairly straightforward. So for instance, taking a look at, well, I guess for component form here, we'll go ahead and add. This is going to be my change in x followed by my change in y. Looking at example 1 here, the first point that we're given, p sub 1, represents the initial point, and the second point, p sub 2, represents the terminal point. We are trying to figure out the movement, the vector that is going to capture that movement. If I'm looking in my x direction, how do I move from 3 to -2? To the left by 5, so that's going to be -5 in my x direction. And how do I get from 1 to 5? To the right by 4. And so this is my vector. And that's it. Take a stab at B and C. We'll take like, I feel like 2 minutes is even too much for here, but we'll say take a minute or two. Figuring out what is my X movement, what is my Y movement, and you really do treat them as kind of their own separate thing. What is my change in the X direction? What is my change in the Y direction in order to get that net movement? Yeah.
Is the quiz on 6162?
6162 will be next Monday.
Monday?
Yeah. All right, so looking at B here, what is my X movement? How do I get from -2 to +2? Increase by 4. And how do I get from 4 to -1? -5 in the Y direction. And then for C, how do I get from -1 to -6? -5. And how do I get from 3 to 7? +4. Notice that A and C are the same vector, right? The initial point being different, the end point being different, that doesn't matter. They are the same vector. B has the same magnitude, and we can confirm that here momentarily, although you could probably figure out what the formula for magnitude is going to be. Yeah, they in fact are the same length. The difference between them is going to be their direction. -5, 4 is going to be pointing into quadrant 2, and 4, -5 would be pointing into quadrant 4. So same R's, but different thetas. And so different vectors. All right, questions with our component form here? Hopefully fairly mind-numbingly Straightforward? It's like, hey, we've been doing this for a hot minute. Okay. Component form is one of, I would say, probably like 3 standard ways to look at vectors. We are only going to really be focusing on component form and then one other. It doesn't really have a name. I'm going to call it like the decomposed form. Basis form is probably the better way to write it, to say it, but we don't know what a basis is. And so we're not going to worry too much about that. The other way is as a column vector. So I'll show you what that looks like. A way that I could represent this 2, 3 would be to say that this is 2, 3, like this. It looks an awful lot like what? Say again? Okay, it kind of looks like a fraction. There's another mathematical thing that kind of uses these brackets that kind of has the numbers on top of other numbers. Starts with an M. It looks kind of like a matrix. And in fact, that is what you would find, is that a matrix can be decomposed into a linear combination of various vectors, and it's its own crazy thing. Take a linear algebra class, and you'll get to suffer through what I have suffered through with regards to that. So that's one way. Generally speaking, that is what you would see in like a linear algebra class, because their focus is on how vectors work within matrices. The other way that we are going to see this is very similar to how we saw our complex numbers, which is as a sum of the x direction movement and the y direction movement. Now for this, we are going to use what are called basis vectors, which again, we don't need to worry about what those are, but they are what we are using. These are essentially going to be direction vectors. They're going to be pointing us in, telling us, hey, this is your movement in the x direction, combined with, hey, this is your movement in the y direction. They don't really interact with each other all that much, but they are kind of a good way to think about what is going on here. The direction vectors that we are going to focus on are called, we will call them I. Notice that I'm using this little arrow. This is not I, the square root of -1. This is I, the direction vector, which is the vector 1, 0. So it only is pointing us in the x direction. And the second direction vector that we will use is j, which is its kind of contemporary 0, 1, or complementary or whatever. We'll look at how we add vectors a little bit on Monday, but the gist is you add the x's and you add the y's. And so if we have the vector 2, 3, we could very easily think of that vector as 2, 0 plus 3, 0, or not 3, 0, plus 0, 3. And notice that 2, 0 is just 2 times I and 3 times j. Which is to say, if I want to follow this movement, if I want to break this apart into its component movements rather than just going start to finish, we need to travel twice in the I direction and 3 times in the j direction. And that result is the same movement that we end up with. The net result here is this exact same thing as going straight to the end. And so we get this, what I'm going to call decomposition form, which is to say that any vector that can be written in this form of x comma y or delta x comma delta y can also be written as our delta x in the I direction plus delta y in the j direction, and you'll see either. You can see either, you can see both. These have a specific name. These are called, again, basis unit vectors, but we'll look at that. We'll look at the idea of a unit vector later. Essentially, unit vectors are vectors that only code for direction because they have just a magnitude of 1. And so here we have a vector that only has a length of 1. It only is referring to either that 0 degree theta or that 90 degree theta, depending. All right, questions here? All right. One more thing that we are going to look at. This is not new. This is basically just the idea of if vectors are defined by their direction and magnitude, then it might be helpful to be able to identify their direction and magnitude. Direction is theta and magnitude is r. There isn't a form for this. Like before, we had like r comma theta for a polar point. We had r CIS of theta for a polar complex number. We don't have a polar vector form. They just are those quantities. Like the value of r for the vector is r, and the value of theta for the vector is theta. And so you would just say what they are, rather than like worrying about presenting them in this different form. And the good news for us is we're looking for r, we're looking for theta. This is going to be exactly what we've been doing this entire week. If I have the vector, we could think of this either in its component form or its decomposed basis form. If I have the vector x comma y, what is r going to be? Yeah, square root of x squared plus y squared. Pythagorean theorem, and also always what we have done for r. And what equations can I use to find theta? Yeah, cosine of theta is x over r, and sine of theta is y over r. So same thing that we've been doing for this entire unit. So let's take a look at example 2 here. We're going to look at 2b. A and B are similar to the example that we did with the complex numbers in that they aren't unit circle thetas. You'll notice that that x and that y don't really look like they're going to line up and give us nice unit circle values. They won't. So not unit circle thetas. If we don't have a unit circle theta, what do we need to do for our, how do we find the theta? What do we have to use? We got to use the inverse trig functions. So A and B would require us to use inverse trig functions. Looking at B, though, what do we notice about where B lives? What direction is our vector pointing in? Negative 5i, negative minus 7j. Where? What quadrant? Third quadrant. And do we have an inverse trig function that can give us a third quadrant angle? No, we do not. Okay. So that's a little bit problematic. So we're going to need to get a little bit creative, kind of on the front end here. So I'm trying to get to the third quadrant. I have a couple of options for angle, therefore. My inverse sine can give me either a quadrant 1 angle or a quadrant 4 angle. Inverse cosine can either give me quadrant 1 or quadrant 2. It's not super easy to go from 2 to 3 or 4 to 3. If you want to think about it this way, the amount that we would have to rotate to go from 5 pi over 6 to 7 pi over 6 is less than the amount that we have to go from 2 pi over 3 to 4 pi over 3. And so there isn't like a clean, just like thing that we can add that'll make it really easy to go from quadrant 2 to quadrant 3. Likewise, the distance between 4 pi over 3 and 5 pi over 3 is less than the distance between 7 pi over 6 and 11 pi over 6. This is a larger swing that we need to take. And so likewise, it is not super easy to go from quadrant 4 to quadrant 3. There isn't just a thing that we can subtract. That's nice and easy. Quadrant 1 to quadrant 3, though, is actually not too bad. What do I need to do every single time to get from quadrant 1 to a corresponding quadrant 3 angle? How far do I have to rotate? Yeah, we just have to rotate halfway around the circle. We could do 180 degrees. What am I probably going to say we should do? In radians, that would be pi. We'll do pi radians. 180 degrees would be fine as well, though. There's nothing wrong with that. Okay, so what we are actually going to do here is we need to get into quadrant 3. We can't do that directly, but that's fine. We are instead going to find the quadrant 1 analog that we are looking for. And then we'll just add pi to it. That'll rotate us straight to quadrant 1. So that's how to know. Okay. So let's take a look here at B. What is my, we're trying to find R, trying to find theta. Let's start with R. What is my R going to look like here? Yeah, this is going to be the square root of -5 squared plus -7 squared, which absolutely correct is the square root of 74. Can't really do much with that. It's like 37 times 2, both of which are prime. Not going to make a whole lot of traction there. We're just going to leave that as is. And so what are the sine and cosine equations that I get? What is cosine of theta and what is sine of theta? Very good. Very good. Okay, so we don't know this, obviously. This is not on the unit circle. No idea what these thetas are that are going to be giving us this. That's okay. We need an inverse trig statement. And this is the bit that's a little bit tricky. We need an inverse trig statement specifically that spits us out where? If we're aiming for the third quadrant, we need to be spat out in the first quadrant. So the goal is Q3. We're going to start in Q1 and then move from Q1 to Q3. Because we can't do it directly. So how do I get to the first quadrant with either my inverse sine and inverse cosine? What must be true about that x value or that y value that I'm plugging into my inverse trig function if I want to be spat out in the first quadrant? They have to be positive, exactly. So we are going to, rather than rewriting these directly as trig statements, which would take us to the second quadrant and the fourth quadrant respectively, we are instead going to take the absolute value. That'll be our reference angle. And then from there, we should be able to just add pi, and that'll rotate us to where we need to be. So in this case, the theta is going to be equal to. Now, if I'm starting in the first quadrant and then moving to the third quadrant, does it matter whether I use inverse sine or inverse cosine? No. I'll use inverse cosine. It doesn't really matter. This is theta of cosine inverse of 5 over root 74. That's my quadrant 1 theta. And so what do I have to do to this? Plus y. Plus y. Or 180 degrees, I would accept that as well. And you could do the same thing for sine. It would be the same angle. It would be the exact same angle. You don't need to. It would be the same thing. Okay. So a couple of pieces of intrigue that we should make sure that we understand. First of all, do we understand why I have this negative 5 over the square root of 74 and why I have used the positive 5 over root 74 instead? Where would the, say again? So that's because we're trying to start in which quadrant? Trying to start in quadrant 1. If we used negative 5 over the square root of 74, where would that start us? Yes, so if we used what we saw here, right, which is negative 5 over root 74, where would that put us? This should put us in quadrant 2 because it's inverse cosine of a negative value. That would put us in quadrant 2. So we cheated a little bit. We said, okay, well, hold on a second. Rather than doing that, let's start in quadrant 1. We're going to use the reference angle. So we'll use the positive version to keep us in quadrant 1. Then we're going to add pi to it. And that will rotate us to quadrant 2. So this is the Q1 reference angle. And this moves us from Q1 to Q3. Yeah, this is our, well, so we have our answer, right? This would be our R. And this would be our theta. And there isn't a form for it. So that's just it. We're done. We circle our R, we circle our theta. There isn't like a vector form for it. Questions? Yeah, similar. So like once we have theta, we're done once we have theta. Good. Oh, so normally you would do, so if it's a unit circle thing, you would just use unit circle knowledge in order to figure out what theta is, and then you'd be done. If it's not unit circle, then you need to rewrite the statement as an inverse trig statement. Now, if we are in quadrant 1, we can either choose to use the sine or the cosine. We don't really care. Both of those would spit us out in quadrant 1. So reworking either of these into their inverse statement would be fine. If we want a quadrant 2 theta, then which of the two trig functions do we need to use? Sine or cosine? Cosine. So if we need a quadrant 2 angle, then we need to use inverse cosine. We would take that first line there and rewrite that as an inverse trig function statement. If we need to be in quadrant 4, which of the two should we use? Sine. We'll use sine to get us into quadrant 4. And if we need to be in quadrant 3 is the hardest one because all the other ones will just get directly mapped there, and that's fine. Quadrant 3 required a little bit of trickiness. That trickiness was we need to first start in quadrant 1. The way I showed it was kind of a cheaty way to do it with the cosine or the sine. You could also do it with tangent though. For instance, you could do inverse tangent of 7/5, which would be positive already. That's already quadrant 1. And then add pi to that would rotate you to quadrant 3. Yeah. Another good way to think about it, you could also think about factoring a negative out at the start. This is what I did with my 4th period. And I wasn't sure that it made it better. But this was like negative 5i plus 7j. And if we want to think about scalar multiplication, we could find the r and the theta here, and then multiplying by -1 is a 180-degree rotation. That's what that scalar multiple does. And so that would then rotate us into quadrant 3. But it boils down to the same thing. You'd get exactly this cosine inverse plus pi. Yeah. Other questions here? All right, we've got a little bit of an awkward amount of time left. So we'll do the rest of example 2 when we get back. I'll give that to you guys to start off on Monday. We should be done with content by Tuesday. Since we have a weird schedule next week as well, I would like to have both Wednesday and Thursday as review days. So we'll have both of those to get ready for the test on Friday. What is due on Sunday? 6162 classwork. What is on Monday? 6162 quiz. So that would be polar points as well as polar form complex numbers. Quiz on Monday.